Hey, this is chapter 10, and as you see, this is about the fundamentals, the principles of metal casting. And in the next chapter, we'll be discussing some specific metal casting process. And in this chapter, our focus will be mainly on the fundamentals of casting process, how casting happens, what are the critical things, what is shrinkage, how we can eliminate it. We will be talking about such issues, such cases in this chapter. And casting, by the way, is one of the popular type of manufacturing processes. We first used it about 6,000 years ago, and with the help of casting, we can even produce some small things like rings, and we can even produce larger parts, products, and even they may have high complexity. In the next chapter, we will see that if you want to increase the complexity, then that means you need to make use of some extra parts, some past special patterns, some extra cores, mold parts. So although it's possible to manufacture, to cast complicated products, it's not easy. And so how casting happens? First of all, we should have metal actually in liquid state. So once it's in liquid state, then what we do, we have a mold, we have a kind of a cavity. We simply pour our molten metal into that cavity and then wait for some time so that our liquid metal will be solidified, and then later in the last stage we will simply remove our part from the mold. And in the next chapter we will see that there are different ways to do this operation. There are die casting, investment casting, many type of casting operations available, and in the next chapter our main focus will be on the types of these, the differences, advantages of these operations. So what are the important considerations in casting operations? First of all, we need to have proper mold. And in the next chapter again, we will see some components of the mold. We need to have gate systems. We need to have screw. We need to have some pathways so that material will be actually flowing into the cavities. Another important thing is the solidification and cooling of our metal in this mold. We should have a kind of a uniform cooling so that we are not going to have any porous regions inside the product. This is important. So for that purpose, you need to have proper designs and you need to have pure kind of material without having any inclusions, any kind of dirt is not actually desired in the molten metal. And lastly, the quality of your molten material is highly important, whether you are using sand particles, whether you are using wood, so they all affect the overall casting process. Now let's focus on the solidification, the main part of casting process. We said that at the beginning of the molding or at the beginning of casting process, we start with liquid metal. And once you pour it into the mold, then we have some sequence of events. There happens lots of events after each other. And once all these events are done, accomplished, then we have the solid product. And so at the end of this process, we want our part to be at room temperature. And these events, actually, these cooling and solidification are depending usually on the size of the grains, the uniformity of the liquid metal, the chemical composition. They all affect the quality of our casting process. And in addition to these, the thermal properties are highly important. The thermal properties, melting point temperature, solidification processes, they are all affected by the mechanical properties, thermal properties of the type of metal we are using. And also the relation, the geometric relation between the volume of our shape and the surface area is highly important. It directly affects the solidification time. We will see that there is a simple relationship between the volume and area, which are directly affecting the solidification time. And lastly, the shape of your mold, the complexity of it, obviously affects the quality of casting process. And in this chapter, our main focus will be on pure metals. We are not going to discuss actually any alloys. You are not responsible from the below regions, from details about different types of alloys. So I will be only focusing on pure metals. Why we are focusing on that is much simpler, since in the pure metals, the melting point and freezing points are clearly defined. So We don't have an actually kind of a transition zone from liquid to solid state, but in the pure metals, we have a kind of a point. After that point, metal solidifies and we only have solid products. And as you see in this plot, we have time versus temperature, and this is our liquid. As you see, it starts to cooling down. Once it reaches to freezing temperature, then solidification happens. As you see, during the solidification, the temperature is constant. And then once this freezing is ending, then cooling of our solid starts. It cools down furthermore to the room temperature, to the ambient temperature. So at the end, as you see, we have solid, and in this in between, in this transition zone, we have liquid, some amount of liquid and some amount of solid. And obviously before that, we have totally liquid metal. Another thing which is important on this figure is the density. And again, we have time on the horizontal axis. So at the beginning of the casting process, we have some shrinkage. So in casting, shrinkage is highly important. It's actually the contraction of our material in the liquid state. We have some shrinkage in the transition stage, and also we have further contraction in the solid state. So due to these shrinkages, we have an increase in the density. And as you see, we have a little increase in the density during our material is being liquid, but there's an abrupt change in the density once we have the solidification. You see at a time in some seconds, this density increases from this value to very high levels. And this is very simple. If you think about ice making, the volume decreases and the density of the material increases. And this actually density increase continues even though you have the solid here, for instance, it continues shrinking, but obviously this shrinkage percentage is not high, it's somehow similar to the shrinkage amount in the liquid state. And so in this process, in this casting process, you pour this liquid metal into the mold, and then what will happen? Solidification will start, and solidification starts from the walls of the mold. So that's why actually we have these little grains at the walls, or we have a kind of an actual skin there, solidified skin. You see this is the top view, by the way. This upper part is the top view, and the lower part you see the side views of some different types of metals during the casting operation. And the first one, the A, is actually for pure metals. You can see around the walls we have little grains, and this is called kind of a skin. And as I said, the solidification starts from these walls, and it goes actually in this direction. As you see, after these little grains, we have some columnar grains being actually formed at the center of our mold. And this happens in the opposite direction to the heat transfer, since heat is actually being transferred from the center to the walls, and this actually grain formation happens in the opposite direction to the heat flow. And during the shrinkage, actually, sometimes we may have some cracks, some porous regions. So that's why actually you should be careful about shrinkage phenomena in this casting operation. Otherwise, if you do not pay attention to shrinkage a lot, then that means you're going to have many porous regions, and this porous regions obviously will affect the strength and will affect other mechanical properties of your casted products. And I think these are all I can say. As I said, you're not responsible for alloys, and you can see things are much complicated in alloys. We don't have such grains, we have such dendrites, and I'm not going to discuss all these issues, but keep in mind that although alloying actually brings you lots of advantages, their solidification stage is quite complicated. You should be very careful while casting such alloys. And you are not also responsible for fluid flow. We will be discussing some fundamentals in the next chapter. Just keep this in mind that this is our desired product at the end of the casting process, but you see we have some extra parts. In the next chapter, chapter 11, we will be discussing the functions of these, but right now assume that in order not to have any porous regions inside, we make use of such extra components, geometric shapes, to perform a proper casting operation. And you are not responsible again from this chapter section 10.4. What you are responsible for from the remaining sections. Now let's focus on these. This one is about the heat transfer. We briefly talk about it that casting is actually kind of a solidification problem, solidification process. So we should be careful about the stages in the solidification, and it's quite complicated. There are many factors actually affecting the quality of this solidification, quality of casting process. We have a mold, and this mold may be made of different materials. It may have different thermal properties. We are using a different molten metal. It may have totally different thermal and mechanical properties. We have a shape of the mold, so it's another issue. So these are the main things we should consider while doing the casting operation. And the flow rates may be another important issue. It should be actually high enough so that we don't actually have any premature chilling or less qualified regions. So its rate should be a bit higher. But on the other hand, if you keep it too high, then what will happen? We will have too much turbulence, and this turbulence will result in some detrimental effects, harmful effects on the quality of your casting again, so that you should find a proper flow rate of your molten metal so that the resulting part will have better qualities, better mechanical properties, and not have any porous regions inside. Now let's focus on the solidification time, how we can roughly estimate the solidification time of a casting process. As we have seen that the casting, actually the solidification starts from the walls, and the thickness of these walls actually depending on the square root of time. So roughly if you actually twice the time you are waiting for initial case, if you multiply the time by 2, then what will happen? The wall thickness actually will be a bit thicker. What is that value actually? It will be thicker. It will be 41% thicker than the initial case. So we can say that the thickness is simply proportional to the square root of time. And this is actually represented with the Cournot's rule. As you see, this is the simple equation for the solidification time. We have a constant C. I will talk about it. And then we have the multiplication of this term here. And inside this term, what do we have? We have volume of our casted product divided by the surface area. So we have a kind of this is actually geometric property. If you have the design of the part, then that means you know this value. And then we have power here, and this is usually taken as 2, depending on some experiments and checking. The people usually use it as 2, but there are different factors affecting this n value. It may be sometimes in between 1.5 and 2. Let's focus on C. What kind of things are affecting it to C? First of all, the type of mold we are using is affecting C. The metal properties, the metal we are pouring into the cavity is highly important, and the temperature of your ambient and the temperature of the molten metal, they all affect the value of C. So if you know C from maybe previous experiments, and if you have defined N, then even though you change the casted product, you can simply determine the solidification time by simply using this equation, Cournot's rule, but obviously that will be a rough estimation. We cannot exactly determine the solidification time, since there are many factors affecting the solidification casting process. So you see, solidification time highly depends on this ratio, volume to surface area ratio. So if this ratio is high, then that means it will take too much time for solidification. But if this ratio is low, then I can say that solidification will happen in shorter time. So it's better if you have some problems in terms of solidification and want to decrease the time for that, then you should update your design such that the volume is decreased but the surface area is increased. So what kind of things we have, for instance, if you think about simple sheet metal, it has a high surface area but very low volume. But on the other hand, if you think about a sphere, it has high volume and it has less surface area. Why is that? Since the volume of the sphere is actually depending on the cube of diameter, but on the other hand, the surface area of the sphere depends on the square of its diameter. So that's why if you have a larger actually sphere, it will be solidifying actually at a much slower rate than a smaller sphere. And we have a nice example about this issue. Please make sure that you have gone through this example. It's a nice example and actually showing you the difference in terms of different shapes, even though they have the same volume. You see, they are trying to cast 3 different products. One is sphere, one is cylinder, one is cube, and they all have the same volume. But obviously, their surface area is different. So you see which one solidifies in shorter time. The cube, as you see, is the best one in terms of solidification time. So in a shorter time, you can obtain this cube. And here we have another, let's say, simple casting process. It's called as slush casting. What is done here? So they start with a kind of a mold, which is in the shape of the resulting product, and then they pour actually molten metal in actually some intervals. This is the case after 5 seconds. This is the case after 1 minute, 2 minutes, 6 minutes. And you see, we don't have a uniform thickness around the walls. And we have actually smaller thickness at the external actually angles, but we have thicker regions, thicker, let's say, walls around the internal angles. Let's focus more on shrinkage again. As we discussed, shrinkage is highly important in casting processes. And if you cannot control shrinkage, then probably the dimensions will not be proper. You have difficulties in dimensional accuracy and tolerances. And furthermore, there might be some warpage, and there may happen some little cracks or internal cracks in your product. So how we can eliminate it, we'll talk about them in a moment. But there are some ways to eliminate shrinkage. And shrinkage happens, as we discussed earlier, while your liquid metal is cooling down, and it happens actually mostly in the second stage during the phase change. So once your metal is actually changing from liquid to solid, we have too much shrinkage. And lastly, it also shrinks while it's actually at the solid state, while its temperature is being decreased, but it's not as high as the shrinkage we have in the second stage. And you can see some shrinkage percentages for different type of materials. You see the maximum one is aluminum, and in some cases, for some specific type of metals, we have expansion. But this is not very common. This only happens on some kind of actually silicon, gray iron kind of materials. And this happens due to the grain growth. The grains are a little bit different. So once they solidify, there is an increase in the volume of these specific materials. Now let's have a look at some defects, some type of defects we may have in the casting process. The first one is the tears. You see we have some tears on the outer surface, and this happens once your actually mold is not actually letting your product cooling down properly, and you can simply solve it by having a bit larger maybe design, or you may have different features on your mold so that these tears are eliminated. And as we said, the porosity is highly important, and this happens mostly due to the shrinkage, and sometimes you may have some gases inside your liquid metal. This porous regions may also happen due to the dissolved gases. And this, you see, we have some examples: a porous region here, another porous region here. So what we do, we have some different ways to actually eliminate this problem. First of all, we may use some kind of chills. You see, this is a chill example, another one chill here. So these are kind of specific materials, so that once we put them here, then we will be increasing actually the solidification rate. So the solidification time decreases and these porous regions are eliminated. Another way of elimination, another way to eliminate this porous regions is to use some extra material, and you can simply do it by using a kind of a reservoir of liquid metal. If you have it in your design, in your mold, then probably these porous regions will be eliminated. And as I show you, we may be using some internal and external chills. So these are examples for external chill, this one, but we may furthermore use some internal chills. And if that is the case, then we should be using the same material with the casting product, so that once they are solidified, the content of our product will be the same. That is an important issue. But if you have such corners, then you may even use such external chills easily at all these corners, so that we are not going to have any porous regions at the center. And furthermore, we may also use some alloys in order to eliminate this porous regions, but it's a bit complicated. You should be aware of all the properties of these metals and then try to come up with a proper solution, proper mixture. And with the help of this alloying, actually, we may be using some specific metals having higher thermal conductivity, so that this heat is actually dissipated. And lastly, as we have seen in the powder metallurgy chapter, we may be using hot isostatic pressing. So if that is the case, then that means we are applying pressure, high pressures at high temperatures. And if you do it, then if you remember, we said that with HIP, we can increase the density. And this is actually the case here. Once we apply HIP here, then these porous regions will be eliminated and the overall density of the product will be improved. And that's actually all for this chapter. Please have a look at these questions, and even you may have a look at some questions regarding the Kolynov's rule. It's quite important. Please have a look at them.